Welcome to qnawire.
Okay, so the question is, we've got some methyl groups, and I'm just going to draw their Lewis structures and show the proton in question. That's 1. Here's 2. Okay, here's 3. Here's 4. And 5. And the question is, which of these will be the most downfield? What is meant by downfield? That means to the left, right? Highest chemical shift. High. Downfield. Okay. How does something end up further downfield? De-shielding. The more de-shielded something is, the higher downfield it is, right? And how is something de-shielded? Electronegative neighbors, or neighbors that will steal electron density from the carbon-hydrogen bond, right? So nitrogen is more electronegative than carbon, right? It's further right on the periodic table, right? So it will, compared to carbon, steal some electron density. Oxygen is even further down, right? It's going to steal some electron density. But notice that both nitrogen and oxygen have lone pairs, and that these lone pairs nearby sort of don't completely counteract the electronegativity, but they're certainly not helping, okay? Oxygen without a lone pair would be even more de-shielding, I'll say that, right? It's not the most powerful de-shielding effect in the world, okay? That's all I want to point out when it has a lone pair. Contrast this with a carbonyl. Here, this oxygen is further away, but notice that its lone pairs are nowhere near this carbon. And if we consider resonance, right, remember that this is in resonance with the following resonance structure, right, in which we put a formal positive charge on this carbon, right? And this formal positive charge is going to be more electronegative than any oxygen or nitrogen would ever be, so supposing they're neutral, right? So the point is that this oxygen is pulling a lot of electron density from this carbon, and that carbon in turn is pulling a lot of electron density from this carbon, right? And whenever you see this double bond to oxygen or double bond to nitrogen, as it is sometimes, just know that these bonds pull a lot of electron density towards them, and therefore will pull a lot of electron density from the neighboring bonds, okay? So it turns out that this carbonyl group that we have here is the most electronegative group or electron withdrawing group in all of these examples. Right, because here we have carbon. Carbon has the same electronegativity as this carbon. It's not going to pull any electron density towards us. Here we have a bunch of sp2 carbons, which because of their increased S character are more electronegative than an sp3 carbon, but it's not as powerful as, say, nitrogen or oxygen, or in this case, a carbonyl, which is the strongest electron withdrawing group amongst all of these options, right? So the answer here is 3. And that's because, effectively, if we just consider the resonance hybrid, this molecule looks like the following, with a partial positive on carbon and a partial negative on oxygen. Right? And this partial positive is doing a lot of work to draw electron density away from this carbon and effectively away from this hydrogen, which de-shields the hydrogen, meaning it moves further downfield, or its signal does.